Hello YouTube, this is Umozo3. For several videos now, we've built up an understanding of sorting algorithms, and we've been learning about bubble sort, insertion sort, and selection sort. And we said that we can basically draw similarities and differences between these sorting algorithms, which work in slightly different ways, but all of them have the effect of basically accepting a list and returning a sorted version of that list. And basically what it entails is multiple comparisons, right? So we usually have a loop inside of another loop, and then within the inner loop we're going to have an if statement or some kind of boolean that we're checking. Okay, and basically what we would check to see is to see whether or not a larger element exists earlier on in the list, in which case we would want to swap it with a smaller element which would exist later on in the list, because the goal is to form an ascending list, right? A list where the elements are in ascending order. And we said that any objects, any elements can be sortable, can be sorted. Okay, and the way that you would do that for a class that you create and define is with the LT magic method. So again, if we scroll all the way down, we have a less than magic method, a less than an LT dunder, which we've talked about in previous videos, but we would say that one person is less than another person if the length of my name is shorter than the length of the other person's name. So hopefully that's clear to you. But we've spent multiple classes now looking at, or multiple lessons now looking at this architecture for the person class. And remember, we also have the length of an instance, so we can define what it means for a length of an instance. So if we say length of u for some instance u, what that would return is basically the age of u, the integer division of the age of u with the length of the name of u. So hopefully that's clear to you. And then you can also treat an instance of a class as though it were a dictionary that you could basically feed keys into and get values out of. And that's what the get item dunder allows you to do. And then the set item dunder is similar, but instead of just retrieving a value at a particular key, you would be reassigning a value at a particular key. So for example, you could go ahead and say self.name equals my val if I specify that I want to go ahead and change the name instance variable. But this sort of architecture is up to you. And we had a silly one in the previous video. What if you wanted to say u of whack equals, something? Well, then that something doesn't matter, because then we're just instructing Python to go ahead and print Wacky Wednesday on the console. But we went ahead and tested that out down here, and we had different examples of that. And then we also said that Lambda functions don't have to accept any inputs. So again, we had this example up here where we had two functions which just return the numbers 77 and 15 respectively. And then we also have a my function 6, which seems to accept two inputs. And the question is, what are the data types of f and g? And so if we look to the right here, it seems like what my function 6 does is it returns the integer division of f over g, right, where f and g look to be functions here. So we would really be looking to do, the result of f over the result of g, but the integer division. So whatever two functions we're passing in, and presumably they would have to be functions that accept no inputs and return numbers. So we talked about that in the previous video. And we also talked about this notion of function reference variables. So we said basically ref4 equals my function 4. So you can say variable name equals function name, and now you can use ref4 exactly as you would have used my function 4. So now you can say print my function 6 of ref4 comma ref5, because ref4 and ref5 now refer to 0 input functions that return numbers. Okay, and so that's what we would stick into my function 6 as the two inputs to my function 6. So then it would go ahead and do the integer division of 77 and 15, and that's why we got 5 printed on the console right here. So hopefully that's clear to you. And we've also been talking about sorting objects, right? Not just integers and floats, but also strings and person objects and point objects, right? And so we use the less than dunder in order to establish what it means to say that one object is less than another object, to say that one instance is less than another instance. You define that with the less than magic method, the less than dunder. So with the bubble sort here, you have a for loop within another for loop, and then within the inner for loop, you have an if statement that you're checking, right? And we talked about that in lesson 48. And then we also had an insertion sort algorithm, and it's very similar. It's a little bit more efficient than bubble sort, but it requires slightly more lines of code. And so we studied the architecture here. And then we also have a selection sort. So this is from the previous video. So now we have 3 sorting algorithms, and you can see it's similar. It's also a for loop within another for loop. And then within the inner for loop, there's an if statement. There's something that you have to check, okay? So we're always thinking about doing comparisons and checking to see whether we have an element that's out of place, in which case we would want to go ahead and do a swap. And that's what happens on line 104 within the context of the selection sort algorithm that we wrote, okay? So hopefully that's clear to you. So then in this video, what I want to talk about is I want to talk about something called linear search, okay? So we're going to be talking about another type of algorithm. But it turns out that we have algorithms not only for sorting lists, right? Not only for sorting collections of elements. We've already spent 3 or 4 videos studying that, right? The bubble sort and the insertion sort and the selection sort. But now what we want to do is we want to turn our attention to something called searching algorithms, okay? If we're given a list or a tuple or a set, how can we basically, well, a list or a tuple is really what we'd be talking about, but how could we find an element within that list? How could we quickly determine the index position of the first occurrence of an element within the list, right? And so what we're going to do, you can think about different approaches there are, and there are probably more than 2 ways to do that in total. But if you're looking at a list of elements and you want to find a 7 within that list, or you're looking in a collection of words and you want to find the word trophy within that collection of words, there's different ways that you can think about doing that. So one approach you might take to searching for an element is to start at the beginning of the list, right? To start at the beginning of the tuple. And you could say, well, let's check the element at index position 0. And then let's check the element at index position 1. And then let's check the element at index position 2. That searching algorithm is called linear search, and that's what we're going to be talking about in this video. But then in the next lesson, we're going to learn another type of searching algorithm that works for sorted lists, okay? So it's going to work for sorted lists and sorted tuples. And basically what we're going to do is we're going to compare and contrast 2 different algorithms, kind of like how we've been comparing and contrasting 3 different sorting algorithms in the previous 3 or 4 videos. So hopefully that's clear to you. But what we're going to do is we're going to look at a linear search function here. So what I do is I have defined linear search of my tuple and target, okay? And so you can think about different ways to search for an element within a particular list, right? If you were looking for a word within a dictionary, right? If you didn't know the definition of the word sky, or you didn't know the definition of the word elephant, what would you do? Would you go to the very beginning of the dictionary and look at all the A words and all the B words and all the C words and all the D words all the way down until you found elephant or sky? No, you would do something a little bit more methodical. Since you're working with a sorted list of words, since the dictionary is sorted according to, you know, the alphabet, there would be a quicker way of finding the definition of the word elephant or sky rather than working your way down alphabetically. So we're going to talk about, that's called binary search if we use a sorted collection and we sort of basically divide our dictionary, divide our list into 2 every time. But we're going to talk about that in the next video. But in this video, we'll be talking about linear search. Okay, so what we're going to do is we're going to basically do a little Blackle search, and we want to learn about basically how this function works. So essentially what we're going to do is we're going to basically say, we're going to go to Blackle and say linear search, okay? And then you can go ahead and look at the Wikipedia article. And so basically this is a computer science thing, right? It's not just a Python thing, but there's also a linear search for the Java programming language. And if you've been following along with the curriculum, you know that I've also done Java videos for all these topics. And I also have a video about how to do linear search in Java, okay? It's the same sort of concept. It's literally identical when it comes to the concept, but of course the syntax is different, right? And so the way that you look at elements and do comparisons and for loops is a little different. But anyway, in general, the linear search is going to apply to multiple different programming languages, okay? And it says in computer science, a linear search, which apparently it's also called a sequential search, but I have yet to hear it called that by other software engineers or within industry. But linear search is a method for finding an element within a list. It sequentially checks each element of the list until a match is found or the whole list has been searched, okay? And so basically what it means is it runs in linear time, okay? So basically if your list has 437 elements, that means that at worst case, it'll take 437 steps to find the element within the list, right? And it says linear search is rarely practical because other search algorithms and schemes, such as the binary search algorithm, which is what we're going to talk about in the next video, allow significantly faster searching for all but short lists, okay? So linear search is great if you're looking at 4 elements or 9 elements, right? You can just look at the first one. Is that the element I'm looking for? No. Look at the second element. Is that the element I'm looking for? No. Look at the third element. Is that the element I'm looking for? Yes, that's the one, okay? But basically, what this article is saying is that at worst, it's going to take up to n checks, right? So if the size of your list is n, it could take up to n comparisons, right? But at best case, you would find it in the very first spot. You'd find it at the beginning of the list. It has a little pseudocode here, so a little bit of a rule of thumb here, basically. But what you would do is given a list L of n elements, okay, with values L0 all the way up to Ln minus 1. So what you do is you think about these are like the values at the n index positions within the list L, right? And you could be talking about a tuple here also, okay? It's not necessarily a list. You could be working with a tuple as well, because when we were talking about sorting algorithms, we were talking about modifying the actual list. But if you're doing a search, you're not modifying the values at index positions. You're simply looking at them. You're just reading them. Okay, so this will work just as well with tuples. And in the examples that we do in this lesson, we're going to be using tuples instead of lists, just to remind you of that. But think about a list or a tuple with n elements, right? With the values, you know, L0, L1, L2, all the way up to Ln minus 1, right? And the target value t, what you do is you set I to 0. And you say if L sub I, so the current element that I'm looking at is equal to T, then the search terminates successfully, right? That means that you found the element. And you would return I. So we would want to basically figure out the index position where an element exists, right? So if we're looking for the number 72 and it occurs at index position 6, then we would want to return the number 6, right? But otherwise, if you haven't terminated the search successfully, if Li is not equal to the target value that you're looking for, you need to increase I by 1, okay? And then if I is less than n, you would go back to step 2, and you would basically go ahead and check to see whether the next element in the list or tuple is equal to the target value that you're looking for. But otherwise, if I is no longer less than n, right, if you get to the end of the list or the tuple, then the search terminates unsuccessfully. That means that you did not find the element. And typically what we're going to do for this purpose is we're going to return -1 if we did not find the element, right? Because if it exists somewhere in the list, it could have been occupying index position 0 or 3 or 7 or 12, right? But there's no way in hell that it would occupy index position -1 if it's not in the list. So we would basically return -1 if the search terminates unsuccessfully, if we don't find an occurrence of the target value in the list or tuple that we're searching through. Okay, so hopefully that makes sense to you. So we define linear search, and we need to accept a tuple or a list, right? But let's say a tuple and a target value that we're looking for. And so basically what we could do is you could make doc strings, and you could say this function accepts an iterable, so we would say list or tuple, and a target value, and returns the index position of the first occurrence of the target value within the tuple according to the linear search algorithm, okay? And you'd have to specify parameters here. So you would say my tuple, the tuple or list to search through, okay? And you could basically also say target, the target value to find the index position of, or something like that. And then you could say returns, and then you would basically say returns, and then you would say the index position of the first occurrence of the target value. And then -1 if it did not appear in the tuple. Okay, so hopefully that makes sense to you. But that's what we would do it by convention. And so what you would do is you would say result equals -1, counter equals 0, found equals false. So you could keep up with a Boolean. So this Boolean keeps track of whether or not we have found the value we are looking for, okay? And by default, the result is -1, default if we do not find the value. So if we do not find the target value that we're looking for, then the result will remain -1 throughout the entire execution of the algorithm. But we're going to start out with a counter of 0, right? And we're going to say, let's do a while loop. So we could say, while counter is less than length of my tuple, and not found. So basically, while I haven't gotten to the end of the list yet, and I haven't found the value that I'm looking for, so both of those Booleans have to be true, what I would do is I would check to see if my tuple of counter is equal to target, in which case it is. If it is, then what I'm going to do is I'm going to set the result equal to counter. So this would basically set the resultant index position to whatever the counter is currently at, right? So if the counter's at index position 4, then it would make the result equal to 4. It would say, look, I found it. And then this would basically switch the found Boolean to true so that the while loop stops, right? Because the while loop depends on found being false. So once you make found true, the loop is going to terminate, right? And you could think about another way to terminate a loop. You could have thought about doing this with a break statement. We're going to see an example of that in a minute. But then what you would do is you would say counter plus equals 1 after the Boolean, right? So basically you would have to, after the if statement, so you would increment the counter regardless of whether or not it was equal to your target value, right? But if you did hit the target, you're not going to keep going through the while loop. The only way you keep going through the while loop is if you haven't gotten to the end of the list yet and you haven't found the value yet, right? And then you would just return the result. So you would just return the index position where you found that element. So what we can do is we can say some tuple equals, and then what we would do is make this a tuple. And so again, you can either do it with parentheses, right? So optionally, we could have had parentheses around them, right? But you could have just said 8, 5, 5, 7, 9, 11, 6. And remember, tuples are not mutable. You cannot modify the values at index positions within a tuple. You cannot insert or remove elements from a tuple. But you would say print linear search of some tuple with 11. And so this is going to return the index position of the, and then we could say first in square brackets occurrence of 11, right? Because there's only one occurrence of 11. But if you had said 5, it would return 1, not 2, because the first occurrence of 5 would be at index position 1. But anyway, what we're going to do is we can go ahead and run main.py here. And so I think we're still printing the result of this selection sort stuff. So let's go ahead and remove that code from earlier. But what we go ahead and do is run main.py, and we have the 5 that was from earlier on. That was from our Lambda function stuff. So let me go ahead and remove that. So now we're ready to see 5 printed on the console. And that's because within this tuple, within some tuple, the first occurrence of the element 11 occurred at index position 5. What if we had made this a 12? Well, now there's no 11 within that tuple, and we get -1. What if we have put an 11 here and an 11 here and an 11 here? Well, then we would just get a 0 because that's the first occurrence of the elements within the tuple. So hopefully that makes sense to you. And obviously this works for lists as well, but again, it works for tuples because this is just a search. We're not changing elements at index positions. We can have a similar linear search, but for objects, right? So what if you were searching for a particular object? So what we're going to do is we remember the person class that we've been talking about for several lessons, right? And we said that every instance of the person class has a name instance variable. And one of the things we made is a get item dunder. And we say we can basically treat an instance of a class as though it were a dictionary that we could put keys into, right? So we could say for some instance of the person class U, we could say U of name, name in square brackets, and it would return the value of the name instance variable for that particular instance U. So what we're going to do is we're going to say result equals -1. So we're going to call this linear person, and we're going to search for the index position of a person object within a list or tuple of person objects according to a target name. So we're going to pass in a string, not a person, but a string, a name. And we're going to say for counter in range of length of my people. So this is a slightly different architecture, right? Instead of using a while loop, we're using a for loop. And instead of keeping track of a found Boolean that checks to see whether or not we've found the value that we're looking for, instead, now we're going to use a break statement. So we would say for counter in range of length of my people, current guy equals my people of counter. So this would be the current person objects at the current index position. So hopefully that makes sense to you. And you would say if current guy of name, right? So now current guy is an instance of the person class. And you would say for that particular instance, if you say if the value of the name instance variable for that particular instance is the target string that I passed into this function, then we would say that the result is equal to a counter. So assign result to the current index position, and you would break out of the loop. So you would stop going through the loop. So stop the loop. And then you would just return the result. So you would just return that index position. And so what we could do, we basically had a tuple of person objects here. So we could say tuple people, right? And then we could say U, V, W, X, Y, Z, and then we could basically say print, and then we could say linear person of tuple people and Z, and then we could get and then we could get basically, what if we said Angela here? So then we could basically search for the particular person by their name, right? So then if we go ahead and put that underneath the definition of the function and run it, then you go ahead and get 5 because Angela was at index position 5. From UMOS03, thanks for watching, and please subscribe.